There we go. We're good? Yep. Okay, so we can look at the life cycle of drops. So we've seen that they can be born by vigorous flow. We've seen this many times throughout the course. So we have basically fluid fracture. So we go from a volume to sheets to filaments. And that's really what was happening here, except we went from sheets to filaments to drops. Well, that's a vigorous flow resulting in in droplets. And so typically so we know how to handle the dynamics of sheets, filaments, and drops. So another possibility is condensation. So just like bubbles can nucleate from dissolved gases, we can get drops condensing from moist air. So this is the origin of clouds, for example. So rain. So you have an updraft of moist air within the atmosphere. Okay, so as it goes upwards, it's cooled. And you get condensation. And clouds. Okay, and you can also, if you have a very vigorous flow, so condensation can be assisted by Bernoulli low pressures. So this is, if you've ever seen the contrails of jets, these are a result of the Bernoulli lows in the wake of jets. Okay, so when you see a jet, you basically you'll see trails of drops. So they'll see clouds generated their wingtips, and this is from the condensation of water. And it's actually, and so this is what allows you to see, have you seen the Crow instability? So the Crow instability is if you have two line vortices, then if you follow them down, it goes unstable like this. But on a very still day, you can see this. So you'll see jet flying over, you'll see a pair of vortex lines, which are made visible by the condensation of water drops. And then this pair will actually turn into a series of vortex rings. So you get vortex rings propagating downwards. Okay, and this is also, so condensation is also assisted by, and this is quite interesting, I think, by solid phase. So this was true also we saw in bubbles. Bubbles tend to nucleate most easily if you have rough solids around. The condensation. You basically have a Bernoulli low, right? So basically the pressure gets so low that the water will come out of the dissolved water, the moist air, water will condense out of the moist air, and it actually happens on the junk, so on the sort of chemicals being spewed out by the plane. So it's actually being assisted.
Why at the wingtips?
Because that's where the pressure is the lowest.
The lowest.
Yeah. So the speed is highest. Yeah. Okay. So again, just like bubbles come out more easily if you throw sugar into your soft drink. Presence of a solid phase will facilitate nucleation of drops. Okay, so and it turns out, so for example, the condensation of water vapor into drops requires higher vapor pressures than found in clouds. So the fact that you get clouds forming actually is dependent on there being dust in the atmosphere, or some sort of solid phase. So it turns out that the prevalence of condensation nuclei in the atmosphere is important for rain. And this can be biogenic, that is to say, it can be spores or some sort of things made from living creatures, or it can be aerosols which are man-made. But I read an interesting article suggesting that there's a feedback between the biosphere and the atmosphere, basically, because, for example, forests will generate lots of spores and so forth. These actually promote rain, right? So, sounds like another theory of Gaia type mechanism. Okay, so for now let's look at the life of drops. So in terms of their dynamics, we can describe them. So now we have something which is heavier than the ambient. Okay, as before, we have Reynolds number, Bond number. Okay, and so when things are very small, and these settle at this is our Hadamard-Rosimsky speed. Okay, and so if we look at what happens as the size increases, so then you get weak distortion into an oblate ellipsoid, and so this is basically the raindrop zone here. But notice that so there is, as in the case of bubbles, there's a viscous boundary layer generated, and so there are pressure variations in the wake, but the inertia of this thing is large relative to the aerodynamic pressures you get, so you don't get very vigorous motion. The reason you get very large motions for bubbles is the dynamic pressures being applied from the external fluid scale like rho u squared, right? So rho is 1,000 times higher in water than air, so a bubble moving through water is going to feel its weight much more than a drop falling through air. Right? So you don't see extravagant distortions. Okay. So you get wake instabilities. Weak deflection because the aerodynamic pressures are relatively low. Okay, and again, as it gets larger, so eventually drop fracture, the aerodynamic stresses. When the bond number is order 1 or A is on the order of the capillary length. And so that's what we saw. That's what we saw here, and we rationalized this earlier. Okay, so the other thing that can happen, this is, I think, a useful physical picture, is to think of drops as springs. So basically there's a natural, they have an intrinsic frequency, which we saw on the first problem set. So if we look at drop vibration, oh, this again. Okay, so if we drop, so here we just release a drop, and you can see it's basically doing this, right? So we started from a non-equilibrium shape, it's kind of overshooting, and so we can ask what that vibrational frequency is, okay? And you did that with the scaling argument. We can take another look at that now, and then so you see basically, but drops have a natural frequency of vibration. So here, and you can use this if you want to keep a drop from, if you want to free a drop, say. So you have a drop, say, stuck on a surface, you can ask what frequency should I hit it at to get it to move, right? How should I hit it? What's its natural, what frequency is going to give me most bang for the buck, right? And it is this natural frequency, which is either. So if you want to free it, you want it to get the thing moving as much as possible, right? And so here we're thinking in terms of de-pinning the contact line. So here, it's the concept of a natural frequency. It's very useful. And so here we can look at it from above, where it's slightly more dramatic. And the natural frequency is going to depend, so it's going to depend on the surface tension, it's going to depend on the...
starting from a circular bubble? Or?
Yeah.
And what's the forcing shaking the table?
Yeah.
Up and down or,
Yeah.
or laterally?
Either one.
Either one?
Yeah, this is, I think, is vertical. But so the drops do have, so they have different modes of vibration, and you can excite different ones by hitting at different frequencies. Okay, so this is a drop. These are drops sitting on a vibrating surface, and you can. So the different modes of vibration have different frequencies. And actually, Lord Rayleigh solved this problem. So we're thinking basically in terms of this. So this is the lowest mode. It's basically this. But basically by hitting at different frequencies, you excite different modes of vibration. Okay, so let's look and see let's look and see at how we rationalize this natural frequency. So if this is our drop, just imagine there's small distortions, but this initial radius is r naught, and this deflection here is x. So imagine we have large Weber number and Reynolds number, so we can neglect viscosity, and we're basically thinking of a balance between inertia and surface tension. Then you have a balance okay, so here there's going to be a gradient in curvature pressure. So this is going to scale like this is the difference in curvature pressure, and so the gradient is going to scale like this divided by r naught, so it's going to look like sigma x over r naught cubed. So we substitute that in here, and you get rho u omega going as sigma x over r naught cubed, and so that gives a frequency. So u is omega x, then we substitute in and we get the frequency. And this guy you guys got in your first problem set, similar scaling, or perhaps something using dimensional analysis. But this is the characteristic frequency in the system, and so we're encouraged to think of these drops as being springs. And again, we can excite by forcing at higher frequencies. You can excite higher modes of oscillation. That's the most fundamental mode, which has that natural frequency, which we can assess for any given drop. And so think of how to most easily agitate it. Okay, so there's a natural frequency. Okay, so if you recall, if you have a linear spring, a mass on a linear spring with spring's constant k, then the period is m over k to 1/2. So we see, as we saw in the case of the soap film last class, the surface tension is playing the role of the spring constant, if you like. Okay, so now we can look at drop impact on solids. So this is a problem that people have looked at to a huge extent, again, mostly in the design of super hydrophobic surfaces. So the sort of picture you have is a drop comes down, and whether or not it merges depends on, so the fluid spreads, and you have a lubrication layer here. So you have to describe the flow within the lubrication layer. But that's basically a region of high pressure. And if this basically the thing is going to come in, splash, possibly bounce back. Whether or not it sticks depends on whether or not this touches down. Okay. So this is the secret to all of these things, including the bouncing drop, including all of these videos here. So basically, this thing is getting thinner and thinner and thinner, and when it gets to a critical scale, and it's around on the order of 100 nanometers. It depends on the surface properties, but at that stage, van der Waals forces come into play. Okay, and so the whole idea in the design of super hydrophobic surfaces is to get the chemistry and the texture right to keep this merger from happening. Okay, and so you can make some headway from scaling arguments, and my French friends have done exactly that. For the low viscosity limit, high Reynolds number. Okay, so if we look at small deformations, this is okay, so small deformations, so something like that. This is coming in at speed u. We have a distortion x, an initial radius a. Then you can balance the anomalous surface area, surface energy, I should say, with so you basically say for a small impact this thing comes down and it bounces. So I'll show you a video of this in just a second. But you basically say all of the initial kinetic energy is going in to surface energy, so it's like being exchanged with this spring, and then it's bouncing back, right? So this is the anomalous surface energy associated with distortion, and this is the initial kinetic energy, right? So again, this is the linear spring model. the drop comes down, it distorts, its energy goes into the spring, and then it pops back. Okay? So that tells us that x scales as rho a cubed u squared over sigma to the 1/2. So this increases with u, as we hope. And the deformation time contact time goes as rho a cubed over sigma to 1/2. And again, this is the natural period of the drop, which is this. Okay, and then, okay, so let's take a look at some of these videos to give you an idea of what's motivating this. So I have tons of them. So more generally, whether or not a drop sticks or rebounds during impact. So we're going to look at some of these large deformation cases, but it depends on the speed of impact and the wetting properties of the surface. Okay, so here we have something which is kind of sticking. Here we see some a drop coming down and basically sticking and dying. And this one here, so this is actually we've got a whole bunch of. So this is interesting because here these are experiments by Sid Nagel, University of Chicago, and they vary the ambient pressure, and so the nature of the splash impacts. So you see this very elaborate, this sheet being shot outwards. It's being shot outwards, and then it's closing kind of like a water bell. But this is the high distortion limit, and we just did the scaling for the low distortion limit. So let's look at some of these, if we can. Slow drop rebound. Yeah. So this is the one we've just described. Oh, come on. Okay. So again, you just have this exchange between the kinetic energy of the drop and the surface energy. So it is behaving more or less like a linear spring. That's very slow. Here is slow. Okay, so it's slightly more vigorous. Fast. So there it actually ruptures. Note the sort of wedding cake formation in the surface. Right? You see the step size. And that's, I believe that's the length scale is the capillary length based on the local acceleration of the drop. Okay, so again, what happens depends on how quickly it hits. We just consider the case of weak impact, so the drop doesn't break up. Here we see fracture. And so it's an interesting question. When is it going to break? When is it not going to break? I was just reviewing a paper which is suggesting that the texture on a lot of plant leaves and bugs is anisotropic with the view to breaking the symmetry of the impact and encourage drop fracture on impact. Okay, what's this one? Water on glass. So again, it does depend both on the texture and on the... Oh.
There's a little water that gets used to the thing. Look now.
Oh, yeah. So again, so what happens on impact depends on the surface chemistry as well as the impact speed. slightly more vigorous. So there it basically goes into a thin layer. And does it rebound back? Nope. It sticks. Oops. So you can ask, when does it stick? When does it fracture? This is again relatively low speeds. So one thing we'd like to get is a criterion for fracture. When is this thing going to actually break? Okay, that one definitely broke, right? So expect there to be a Weber number criterion, right? Again, I think, so these are changing the surface chemistry. So this one's a little more hydrophilic, right? The drop wants to stay on it. So you need...
I have this DVD, but I've never realized that you can do a playlist with it. So
Oh, it's quite pretty handy, yeah, for teaching. Yeah, so that one sort of spreads and then sticks.
That was fluid on fluid or was it fluid on solid?
No, these are all fluid on solid. Okay, so we can... you can see these all look, right, the instabilities are pretty similar. Like it looks like some Rayleigh-Taylor or maybe Rayleigh-Plateau along the edge, right? You're basically getting the spreading pancake and this instability in the front, which is going to be one of these two instabilities. Seem to have an endless supply of these. So that's the other possibility, is this, in this splash, you can have really, in this filament that bounces off the surface, you can have that going unstable to Rayleigh-Plateau. That one's just splashing and dying. Okay, so I think we've had enough splashes here. Oh! Ooh. But again, you sort of get the feeling that you can approach all of these problems with what we know, the basic ingredients, right? You have Rayleigh-Plateau, Rayleigh-Taylor, Kulik speed. So that one's definitely fracturing. What's happening on this one? Okay, so we can do... Okay, so this is more interesting now. Okay, so this is very high speed. So I was mentioning this guy, Siggy Thordarson. He has the fastest camera, so he managed to always go an order of magnitude faster than everyone else. But you can see there, when the thing hits, there's this sheet ejected, right? It's not at all clear why that should be. So that happens actually with drops hitting solids as well as drops hitting fluids. And you can understand the dynamics of these sheets. So actually what's happening, there's a shock. If this thing is going fast enough, there's a shock forms at the impact. And this gives rise to very high pressures, and when these pressures hit the sides of the drop, they basically eject this sheet. So let's... Wait, I think this is coalescence cascade. Okay, that's not it. Okay, stop. Okay, so So we've basically seen that there's a huge, there's quite a large array of sorts of things that can happen for the large deformation limit, but none of them look too unfamiliar. We can hope to rationalize many of them. And we don't have much time. I'll just mention droplet. Okay, so in this high speed limit, then when the drop hits, there's actually a shock wave generated at the point of impact. So this is a geometrical effect, so it has to do with the fact that you're hitting a sphere. If you've ever heard of the water hammer effect, but in any case, you get a shock. And so the characteristic pressure is you'd expect it to be rho u squared, right? But it's actually it goes like rho u times the speed of sound in the drop. So this is considerably larger. And because of this, when this shock hits the edge, you get this sheet ejected. So you get this high-speed sheet, and you can tell it has to be vigorous because it's incredibly thin, right? So it's saying that the pressures have to be enormous, so you get this sheet ejected, and this sheet will then act like a water bell, effectively, and it will go unstable. To microdroplets. Okay, and the other, and then we can look at the depth of drops, and we've seen already our coalescence cascade. So I never tire of watching this one myself. So this is again just putting water on water. Yeah, that wasn't a TV show. What's this one, by the way? Oh yeah, this is a close-up of what's actually happening during an individual merger. Okay. So you see their capillary waves swept upwards, and that's the whole secret to why the drop jumps, because these capillary waves are swept upwards and they transfer momentum and give the thing a kick, right? And that's why the drop seems to jump up in the air. Oh, and so here's our last death of a drop is the splash. And you can see it dies, but it creates other droplets. And this is the oh yeah, and then this is called a Worthington jet. Okay, so when a raindrop hits water, you get this jet coming up afterwards, because it basically gives rise to a depression, and then it snaps back because of surface tension. So you get this long thing, and this will then pinch off into droplets itself.
But what's the difference? Basically, between this one and the other one, the one before is the drop came more nearby.
Yeah, you just dropped it very close, yeah. And here it's coming in very high speed.
The drop actually does more of this than
Yeah, exactly.
the previous
Yeah,
one.
but notice it. So yeah, if you do this one, then you get, so that's high speed. That's like a raindrop. But then there are all these other little drops. And those other little drops will come down at low speed. And then you'll see, yeah. But this is a classic. In fact, so the first use of the high-speed camera was to visualize this flow. This is done by Worthington.
The crown, right?
Yeah. No, actually, this.
This thing? I thought
Yeah.
the crown came before this.
No, in fact, this was even before high-speed video imaging. This is just for, I think, fast photography. So using, yeah. So they used to do things. So they just have the camera basically exposed, but they'd flash light just for a split second, so they'd capture one image. That's how they used to do high-speed imaging, right? So it wouldn't be by varying the shutter would just be wide open, but then they just flash light on the system.
Oh, I see. The light is much faster than the shutter, right?
Exactly, yeah. And so, right, so that's basically the end, so the death. So now we can understand this again, the drop. When it merges, the capillary waves, which we saw, would sweep upwards and give it a kick. This is, I think, the best one. I think it goes 6 times, which is pretty good. But has any of you seen this in your coffee? You've got to look for it, because you can see it. If you look carefully. When you're pouring milk into coffee, you'll see this. Yeah. There's the sound. And here they did a really good job lighting it. So they lit it with red on one side and yeah. Yeah, it's fake. It's totally fake. Yeah. Okay, and so in this class of flows, so we saw this is the Worthington jet, which you get after a vigorous impact. This then just pinches off, so it retracts, not due to gravity so much as due to surface tension. You can pinch off due to surface tension. And also keep in mind, when we saw these drops coalesce, so when they coalesce, the moment that they coalesce, there's very high pressure within the drop. And so they actually generate a subsurface vortex. So you get this very vigorous flow beneath them. And these are some of Siggy's high-speed images of sheet ejection. This is a water drop hitting a water surface. And again, you get this, I think it's a shock effect, and you get these sheets being ejected and then rolling up, and you can then treat the dynamics of the sheets as if they're using the water bell equations. And then, so this is what we've seen, basically raindrop hitting a puddle. You get this sort of cascade of small drops forming in sheets. So we can answer all of these questions now. So these are questions which I asked in the first class, and you can basically rationalize almost everything you see. And so this Martin Waugh takes beautiful images. So this is now the Worthington jet. So it's one drop has already hit. The Worthington jet is going, and then he releases another drop which impacts with that. And so this is the Egerton crown, and I forbid any of you from ever writing a paper about that subject. I've already forbidden you many times because we know what's going on. I keep getting papers to review. It's like, oh, we finally solved this long-standing mystery. It's not a bloody mystery. Excuse me. It's not a mystery. We know what's going on. It ejects the sheet, and we can predict the number of size, right? So we have the sheet speed. We can use the water bell equations, and we know that this goes unstable to Rayleigh plateau, which gives us the spacing. Okay, and so we were back on Martin Waugh. So he has now this Worthington jet is coming up, and this drop is coming down, and so they impact. So it's just like our two jets.
So you guys more or less the timing to do it?
Yeah. And so that's what gives rise to this, right? So this is like, if remember we had two jets colliding, you give rise to a sheet in the plane perpendicular, and the rims develop and go unstable to rarely plateau. So these are very beautiful images, but we know the physics, right?
Nice cocktail drinks, huh?
Yeah. These are great pictures, but there's a new kid on the block who I just discovered who took these. So it's called Fluid Drop Art. He has a web page, unbelievable. But this is clearly the same business. It's basically a Worthington jet colliding with another drop, and we can predict that wavelength. And it's very nice. But again, the physics we know, we understand. And then, what's that? Yeah, so I mean, if you use milk and just put in this looks like fluorescein. So I don't expect he photoshops them. I mean, the interfacial flows are very nice to photograph.
So this is not Photoshop. He puts like a color
Yeah.
here and a color
Yeah, yeah. And this is his best. I mean, I showed this one to you guys yesterday, but this is classic, right? What is going on with this one? But if you shoot enough of these things, you'll probably see anything.
There's a little bit of a Star Wars touch.
Exactly. So that's it on drops and bubbles. And we'll do biology next class. So biocapillarity. So all of this, we'll see how what we've learned in the course allows us to rationalize the behavior of bugs and birds.
The ones they talk, I'll make the title in an abstract myself, okay?
For which? What? Soccer one? Yeah, and then Wednesday I'll do the talk on soccer. So there's very little to do with surface tension. I'll try and get it in somehow. Yeah, all right. Okay, very good. Have a good week.